Good morning. In this session, we will continue our discussion about the bar magnet. In the last session, if you can recall, we have seen what happens if a bar magnet is placed in a uniform magnetic field. When a bar magnet is placed in a uniform magnetic field, the magnet experiences a torque. And the equation is given by torque is mb sin theta. Also, we have seen the potential energy stored in the bar magnet is minus mb cos theta, where theta is the angle made by the magnetic moment with respect to the direction of the external magnetic field. Now we will see when we can say that the magnet is in the stable equilibrium position, or when we can say that it is in the most unstable equilibrium position. First I will write the equation for potential energy, then from there only we will see what is the stable condition, equilibrium condition, and what is the most unstable equilibrium condition. Now potential energy stored in a bar magnet making an angle theta with the direction of the magnetic field. Is us minus mb cos theta. Now when theta is 90 degree and theta is 0, theta is 180, so we'll put different values of theta and we'll see what happens to potential energy. First we'll take when theta is 0, then us minus mb, because cos 0 is 1, or the bar magnet placed with dipole moment m normal to the direction of magnetic field, it does not possesses any potential energy. So u is equal to, sorry, this is u is minus mb, so we can call it as this is the minus, so this is the minimum potential energy, because minus mb cos 0. Now when you apply cos 90, you will get u is 0. So this is the case when m and b are parallel to each other. So when a bar magnet is placed with its dipole moment parallel to the direction of the external magnetic field, it possesses minimum potential energy. So this is u minimum, minimum potential energy position. Or this is the most stable equilibrium position. Most stable equilibrium position. That is the case when bar magnet is placed in such a way that magnetic moment makes an angle 0 with the magnetic field, or the magnetic moment is along the direction of the external magnetic field. Now in the second case, when theta is 90, cos 90 is 0, so you can say u is 0, or this is 0 energy position. When b is like this and the bar magnet is placed such that m makes an angle 90 degree, you get 0. When the bar magnet is placed with its dipole moment making an angle 90 degree with the direction of the magnetic field, it does not possesses any potential energy. So this is called as 0 energy position, because bar magnet does not possess any energy. Now the last case when theta is 180. So US minus MB cos 180. Cos 180 is minus 1, so this will become plus MB. Minus MB 0 plus MB. So this is a maximum energy position, U max. Here we got U minimum minus MB, but now U max plus MB. Now when the bar magnet is placed with its dipole moment making an angle 180 degree with the direction of the magnetic field, M and B are antiparallel to each other. M is antiparallel to B. It possesses maximum potential energy, or I can say that it is the most unstable equilibrium position. Most unstable equilibrium position. Now three cases: most stable equilibrium position, most unstable equilibrium position, and zero energy position. Now next, you can also show that a bar magnet exhibits a simple harmonic motion. Bar magnet exhibits, you can show that a bar magnet exhibits a simple harmonic motion. Now consider a small bar magnet which is placed in an external magnetic field B, or this can be, you can show it using a compass needle also. You can take a needle which has a moment of inertia of I. Small magnetic needle, so the which has a moment of inertia I. You can take either a small bar magnet or a compass needle also will be fine. You can show that it exhibits simple harmonic motion. So you can consider a compass needle with moment of inertia I. Now if it is rotated under equilibrium, okay, or I can say that a bar magnet is placed in a uniform magnetic field B and it is under equilibrium condition. Now if you rotate this bar magnet or this compass needle by an angle theta, then you know that it experiences a torque, or I can say that the needle experiences a restoring torque, and the restoring torque will try to align it in the direction of the magnetic field. So the restoring torque is given by restoring torque minus MB sin theta, or under equilibrium condition I can say that under equilibrium condition, if I is the moment of inertia, then it is of this magnet, I into d square theta by dt square minus MB sin theta, or I can say d square theta by dt square minus MB by I into sin theta. Now this represents a simple harmonic motion. SHM, simple harmonic motion. The square of the angular frequency omega square is mb by I. Next you write the square of the angular frequency omega square as mb by I. Or the time period t is 2 pi by omega, which is equal to 2 pi divided by square root of mb by I, or equal to 2 pi into square root of I by mb. 2 pi into square root of I by mb. So the time period of the simple harmonic motion is given by 2 pi into square root of I divided by mb. T is 2 pi into square root of I by mb.